All right, so let's take a look at two examples on graphing log functions. So we're asked to determine the parent function, describe the transformation, and then find all these other details, vertical asymptote, domain, and x-intercept, and finally sketch, okay, by hand. All right, so the parent function, right, is basically f of x is equal to log base 2 of x, okay? So hopefully you can see that, right, without the 3, without the minus, without the vertical stretch, without the vertical translation. All right, so once you have the parent function, right, what I would do is rewrite this as negative x plus 3, which means I can factor out the negative. So let me just rewrite the original function for g one more time. I can rewrite it like this. And the reason why I want to rewrite it like this, right, it's easier to see the transformation, okay? So going from left to right, this number right here, the absolute value of a is greater than 1. You know it's a vertical stretch by a factor of 2. This guy right here, right, this is your negative in front of the x inside the argument. This tells you it's a reflection over the y. So technically, you know, we can call this a horizontal shrink and stretch factor, right? This would be a b, right, based on your transformation notes. But, you know, just to keep things simple, I'm not going to use the horizontal shrink or stretch factor. But if there's a negative in front of the x, you know it's a reflection over the y-axis. And, of course, this is your h, right? This is your k. You're shifted 3 units to the right and 1 unit up. All right, so that answers the first part. How's the transformation from f to g completed? All right, now we're going to find the vertical asymptote. The way you find the vertical asymptote is you set the argument, right, what's inside the parentheses over here for log equal to 0, and you solve for x. You're going to get x is equal to 3. The way you find a domain, right, it's related. You set the argument greater than 0, and you solve for x. Okay, and I explain why that is, right, because you can't raise the base of a log to a power such that you get your argument less than 0. All right. Now, the x-intercept, this part right here, right, how do I find the x-intercept for any graph, right? I set my f or g of x equal to 0, I set y equal to 0, and I solve for x. So this is the part right here where it's a new concept that I will further explain in detail in future lessons. And when I set my g of x equal to 0 and solve for x, right, notice this is actually a log equation. Now, how do I solve a log equation? When you have a single log like this, the key is to get this log by itself. Okay, so what I put here in parentheses, get this by itself. And how do I get it by itself? Well, you move the 1 over, right, and you divide by 2, right? So this is negative 1 over 2 equals log base 2 of 3 minus x. Okay, so again, basic, adding, subtracting, and then dividing by 2. That's how I get the log by itself. Now, once the log is by itself, right, I still need to get x by itself. And the way you get x by itself is not divide by the word log base 2. Again, log is not a variable, right? Log represents an exponential. Is way 1, you could use your inverse properties. Okay, so I'm going to exponentiate both sides by base 2, right? Because I need to get rid of this log word. And the way you get rid of it is you exponentiate both sides by this base of this log. Well, how does that get rid of it, right? 2 raised to log base 2, right? It just becomes the argument. And so, without using a calculator, right, your x, in this case, if I move the x over here, this is 3 minus 1 over the square root of 2, right? This will be the exact value of your x-intercept. And if you want to use a calculator now, right, x is approximately equal to 2.29, right? This is the approximate value, right? So again, you could use Desmos to check, but on a quiz or test, right, I would ask you to give me the exact value. Okay, so you just leave it like this, but approximately 2.29. Now, what is way 2 for solving this? Once you get down to this step again, right, where it says negative 1/2 is equal to log base 2 of 3 minus x, you could just, right, go directly from, log base 2 of 3 minus x. Remember, you did a bunch of problems converting from log form to exponential form. You could just convert this and say, oh, this is just, 2 to the minus 1/2 is equal to 3 minus x. Okay, so if you went directly from here to here, that's okay as well. Okay, but traditionally, most textbooks have the inverse property applied to get to this line. But if you just went from here to here directly, that's fine as well. Okay, so you'll get the same exact answer. So it's really not two ways. It's just one way is you're using the inverse property. Another way is just you're going from log form to exponential form. Either way is fine. Okay. All right. Now we have 1 point on our graph currently, right, which is the x-intercept. And what I want to do right now is, practice plugging in smart points. Okay. So what do I mean by plugging in smart points? So over here, we already have, 2.29 comma 0. And if I go back to my original function, let me just write it down here. My original function, g of x, is equal to 2 log base 2 of 3 minus x plus 1. Without using a calculator, right, how would I plug in points and evaluate? You're like, well, I have to use a calculator. Well, you don't. Would you agree that the way you pick smart points, right, is if you evaluate log base 2 of 2, right? That's easy to evaluate. That's just 1. Or if you evaluate log base 2 of 1, right? That's also easy to evaluate, right? This means 2 raised to what power gives you 1? Clearly it's 0. So if I somehow make the argument equal to 2 or 1, that's going to be an easy point to plug in. So what do you mean by that? Well, if I make the argument somehow equal to 2, right, or if I make the argument somehow equal to 1, that's the x value I want to plug in such that it's easy to evaluate. So what are you talking about? Well, if I solve for x over here, I'm going to get x is equal to 1, right? So this is a point you want to plug in. And if I solve for x over here, I'm going to just get x is equal to 2, right? And you will see that these points will be easy to evaluate. So if I plug in g of 1, right, g of 1 is 2 log base 2 of 3 minus 1 plus 1, 2 log base 2 of 2, right, plus 1. Well, log base 2 of 2, right, we just said that's easy to evaluate. That's just 1. So that's 2 times 1, right, plus 1, which is 3. And if I evaluate g of 2, right, another easy point to evaluate, log base 2 of 3 minus 2 plus 1, you're going to get 2 log base 2 of 1, parentheses, right? Log base 2 of 1, we know that's just 0, right? And so over here, you're just going to get 2 comma 1. Okay, so you have more than enough points. You can graph this now on a set of axes. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so back to our original problem right here, right? We said the vertical asymptote in this problem was just x is equal to 3. And so if I graph that, x is equal to 3. And we have our 3 sets of points, right? 2.29 comma 0, maybe somewhere over here. We also had 1 comma 3 somewhere over here, and we had 2 comma 1, 2 comma 1, maybe somewhere over here. Okay, so roughly the graph is going to look something like this. Now, Mr. Zhu, how do you know that the graph's going to curve like up here like this? How do you know that? Well, for one, I know the transformation, right? Because the graph of log base 2 of x, right? If you were to roughly sketch it, looks something like this. And remember, we said we're reflecting this graph over the y-axis, right? So this is your y-axis. So if you reflect it across the y-axis, right, it's going to look something like this. So therefore, I know the shape of my graph is going to curve this direction. Okay, so know a little bit about transformation, know a little bit about solving log equations, and also know about plugging in smart points to help you evaluate. That will help you graph